in the case of cyclic structures, we can have cycloalkenes, or cycloalkadienes. In this case, in the third example, as you can see, there is one double bond, so it belongs to alkene group. So the name ends with ene. The chain has 6 carbons, so it's hexene. The structure is cyclic, so it's cyclohexene. However, we have 2 branches. I have one methyl group here and one methyl group here. In this case, if you remember, we said we number the carbons from the end which is closest to the double bond. So this is closest to the double bond. I number this as a first, and then I'll go this way. 1, 2, 3, 4, 5. So on the first one and on the fifth one, I have these 2 methyl groups. So I have 1, 5 dimethyl cyclohexene. Okay, that's the name of the structure. Okay. These structures are chemically as reactive as their open chain. Okay, so 1,5-dimethyl cyclohexene is very similar to 1,5-dimethyl hexene in terms of reactivity, but they can undergo into 2 reactions. One is the addition reaction, which the double bond will be eliminated, and then cleavage reaction, which the whole circular structure or cyclic structure will collapse. Okay, so if something wants to happen to this structure, what happens is first it's going to lose its double bond. Some structure will attack this, like the oxygen or hydrogen, and then this double structure will break, and then it becomes cycloalkanes, and then the next one will basically, the cyclic structure one might just break. So the first one is called addition reaction, and then the second one, when the whole cyclic structure collapses, called cleavage reaction. Okay. So so far we studied the alkanes, which were paraffins, all single bonds; alkenes, which we had the one double bond; alkadienes, which we had 2 double bonds; alkatrines, where we had 3 double bonds; alkynes, when we have triple bonds; and then cyclic aliphatics, which are cycloalkanes, the alkanes with the cyclic structures; cycloalkenes, alkenes with the cyclic structures; and cycloalkadienes, which is alkadienes with the cyclic structures. But one might ask why we don't have cycloalkatrines. Like here, I have one double bond, I could have second double bond here, and I could have 3 double bond here. Okay, why we don't have that? Actually, we don't put that. We do have that. We do have cycloalkatrines, but we don't put this in this structure because it turns out that if I have 3 double bonds in this structure, remember how we classified this? We said the more double bonds you have, the weaker the structure becomes, and you need to have the adhesion bonding, which basically adhesion reaction, which you remove the double bonds and go into the more stable condition, which is a single bond. But it turns out that if you have a structure like this, like having 3 double bonds in the cyclic structure, this structure didn't show more reactivity compared to cycloalkadienes. It shows more stability. So it was going out of that trend that we were saying, that we look at the number of carbons, and then we look at the number of the type of bondings and number of the double bonds and the triple bonds and so on and so forth. But here it seems that this structure is even more stronger than the cycloalkadiene and cycloalkenes. Okay, therefore we couldn't put this in that series. So we completely separated these structures, and we said these are different. So we classified the hydrocarbons to aliphatics and aromatics, and these structures are called aromatic hydrocarbons. Okay, and the aromatic hydrocarbons are the hydrocarbons which do have a structure which we call it benzene. So this cyclohexatriene, okay, is called benzene. Okay, So any structure which do have this benzene is called aromatics. Okay. So the first member is benzene. The benzene can have branches. So if it has a methyl branch, we call it toluene. If it has two methyl branches, we call it xylene. So these two branches, they could be placed at different locations. This branch could be here, here, or here. So there are three different type of xylenes also. So these are ortho, para, and metaxylenes. Okay. So benzene groups, we just separated them from all the aliphatics and we just put it on a new category. We call it aromatics because these are more stable. The benzene is a flat and symmetrical hexagonal ring with bond angle of 120. At first, chemists thought the benzene is a cyclohexatriene. However, it has a stable structure unlike cycloalkatrienes. Okay. The benzene ring is retained in many reactions. Therefore, the double bonds in benzene ring must be much more stable than the previously discussed double bonds. Therefore, we just separated them. Actually, what happens is when people investigated this, they found that it doesn't seem that this carbon has a double bond and then this carbon has a single bond and then this one has a double bond. It seems that all these six carbons, they are sharing the same type of forces and they have same 1.5 bondings, okay, between each other. Okay, so it's very symmetric, very uniform. Okay, and people, they call this hybrid bonding. Okay, so some nomenclatures, some structures of the aromatics. So as I said, this structure is called benzene. You can show the double bonds or you can just put a circle inside this structure, and then that's again the same concept. So I see the benzene group. So this is benzene, and it has a ethyl as a branch. So it has a branch on the first carbon, and then the branch has itself two carbons. So it's ethyl benzene or bromobenzene or nitrobenzene. Okay. Benzene can also appear as a branch itself. So in a longer chain structures, the benzene can appear as a branch. If it appears as a branch, we call it phenyl. Okay. So if the benzene appears as a branch, we call it phenyl. Here, basically, we have two phenyl groups coming together, so we call it biphenyl. Okay. So here there are more examples, some examples that the benzene appears as a branch. So I look at this structure, all single bonds though, so they belong to alkanes. The name ends with A and E. I have 2, 4, and 5 carbons in the straight chain, so it's pentane. I need to number them. I number them from the end closest to the branch, so it becomes 1, 2, and 3. On the second, I have a methyl, and on the third, I have a phenyl group. So I have 2 methyl, 3 phenyl, pentane. Okay. Or here, I have a double bond. I know this belongs to alkene, and name it ends with E and E. I have 3 carbons in a straight chain, so it's a propene. And I have the phenyl group on the third carbon. Again, remember, we number them from the end closest to the double bond. So it's 1, 2, and 3. So I have 3 phenyl propene. Okay. As I said, the benzene group, if it has one methyl branch, it's called toluene. If it has 2, it's called xylene. But the xylene could be ortho, meta, or paraxylene. Orthoxylene is more stable than metaxylene, and that's more stable than the paraxylene. Okay, so these are different xylene groups, different xylene members of the benzene group. Okay. And these aromatics, like benzene rings, they can generate a very, very long chains. They can come together and generate a very long chains, like here, having 7 carbons together, having 10 carbons coming together, and they can be very complex, like these structures. I don't expect you to memorize these or, name these. We are just going to have some basics, conventional, simple samples of these. You just need to know, if I see this structure, this belongs to the aromatics, and that's good enough for us. Okay. However, the simple cases like these Ortho, meta, and paraxylene, these are very simple, like benzene group with two methyl groups, or toluene, benzene with one methyl group. These are very simple, and I expect you to know these. Okay. Actually, this was a closed book exam. I generally ask to students to draw different type of xylenes. Okay, and rank them based on the stability. Okay, so these are very common questions. So properties of aromatics: these compounds contain benzene rings. They have pleasant odors, however, they are very toxic, some carcinogenic. Inhalation of their vapor should be avoided. Aromatics can participate into many reactions which do not affect their ring structure. Volatile aromatics are highly flammable. Okay, so these are the properties that we need to know. So this these were all the hydrocarbon components and their classification. So we divided the hydrocarbons to aliphatics, and then we divided the aliphatics to alkanes, alkenes, alkynes, and cyclic aliphatics. And then the aromatics for benzene was different, homologous series. Okay, but in addition to the hydrocarbon components, we said we have also some non-hydrocarbon components. We said nitrogen, carbon dioxide, or hydrogen sulfides are very common non-hydrocarbon components. Okay, the petroleum fluids contain hydrocarbons in which sulfur, oxygen, and nitrogen are combined together. These are basically very common in the oil and gas industry, and they are basically building components or the structures which we call it resins or asphaltenes. Okay, the quantity of resins and asphaltenes are high. They are as much as 50% of the total molecules in the heavy oils. So we need to know their properties, and we need to be able to identify these resins and asphaltenes. Okay. The sulfur component is very tricky because we know the hydrogen sulfide is very corrosive. Okay, so we don't want that to be in our system. But when we have that in our gas, like we have hydrogen sulfide, then we call that sour gas. Okay, so when you hear people, they call it sour crude or sour gas, they refer to the crude oil, or they refer to the gas which do have the hydrogen sulfide. Okay, so this is very very important. And how this happens, they generally come in the form of what we call RSH, okay, which is the hydrocarbon component plus sulfur and hydrogen. Okay, so SH connected to some hydrocarbon component. Okay, this is how they show up in the oil and gas. But the major difference between the resins and asphaltenes are the asphaltenes, they do not dissolve in petroleum. Okay, so they are dispersed as colloids. So they stay in the they separate from the petroleum. They are not dissolvable. So since they are not dissolvable, they will be settled down at the bottom of the separation tower. Okay. However, resins are readily dissolved in petroleum, so they can show up in any stage. Okay. So asphaltenes, they are their part. They precipitate. They are not dissolved in petroleum, while the resins they dissolve in the petroleum. Okay. These are their differences. These both of them can be formed by oxidation of polycyclic aromatics hydrocarbons, and both can be reduced to hydrocarbons by hydrogenation, which basically yields the hydrocarbon molecules H2S and water. Okay. So as I said, in the industry, people they usually refer to paraffins, alkanes to paraffins, and cycloalkanes to naphthalene, and benzenes to aromatics, and resins and asphaltenes. These are very important part of their the classification. And here in this example, it's just a Hilloshow cell, which shows the precipitation of the asphaltene. The Hilloshow cell is simply two glass they put together, and in between they have the glass beads. It's like a transparent cross media, and then they put the oil and then heat it up, so the asphaltene precipitates. So they see that. Okay, so that's end of our lecture, lesson 1, and I'll see you in lecture 2.